Let's say that we have the following circuit. Where we have a 120 volt RMS source operating at 60 hertz. And that voltage is applied to the primary windings of a transformer, like so. And our transformer has a ratio of 10 to 1. So that step down voltage serves as the input Vn of t to the following diode network. And I have to make sure that I'm drawing these in the right order so that this makes any sense. Oh, I'll be damned. I found my piece of paper. Great. And our load in this case is a 0.5 millifarad capacitor in parallel with a 100 ohm resistor. Then we take our output voltage across that network. So my question to you guys is, if we're using a constant voltage drop diode model of VD on is 700 millivolts. That is, I believe, the only information that I need to provide you. What would our ripple voltage be? So the first question that you should really ask yourselves here is, which of the 3 different types of rectifiers that we discussed Wednesday is this? Is it a half-wave rectifier? Is it a bridge rectifier? Or is it a center tapped full wave rectifier? Bridge, okay? So for a bridge rectifier, our ripple voltage is given by 1/2 V peak minus twice VD on divided by RC times our input frequency, right? That's our equation for our ripple voltage. So factor 1/2, pretty straightforward. What should our V peak value be?
Our Vn is 12 volts.
12 volts RMS. So what's the peak value of 12 volts RMS?
12.
I disagree. 12 times the square root of 2. All right. And then we're going to have twice VD on, so that's twice 0.7 volts. Obviously, our R in this case is 100 ohms. Our C in this case is 0.5 millifarads. And our frequency in this case, 60 hertz. And so if we plug in our numbers here, we wind up getting 2.595 volts of ripple. Okay. Yeah, it is a lot. So how does that value compare to our P, right? So what's 12 squared to 2? That's going to be 12 times 0.07, or excuse me, I guess it'd be, no, 12 times 1.4, right? About 17. And then let's call it 2.5 volts. So what percentage is that? 2.595 divided by 12 squared root of 2. 15%, roughly. Yeah. So that's a pretty large ripple, right? So we would see that our output should go from, let's see. So what would be the maximum value of our output in this case?
It would be R 12 squared minus VDR.
Minus 2 VDONs, right? So our Vmax would be 12 root 2 minus 2 times 0.7 volts. $15.571 volts. And then okay, so it's about 16 to 17% of our maximum value there is our ripple, right? Because obviously our minimum is going to be Vmax minus V ripple, because V ripple tells us the amplitude of how far the signal decays, okay? All right, so what if we wanted to force the output ripple to be less than or equal to 1 volt? We obviously need to add a capacitor. So what value capacitor would we want to put in? If our load resistance of 100 is fixed, how would we go about doing that? Yeah, literally take this equation and solve for the total C needed, and then subtract from that our 0.5 millifarad that we already have there. That would tell us what additional capacitance we need to put in to fix our ripple voltage, right? So we can do that pretty trivially, right? So just using simple manipulation here, C would be, so if I multiply both sides by C and I divide both sides by ripple, I should have 1/2 V peak minus twice VD on, all over, why is my brain not working? R V ripple FN, right? Is my algebra correct here? Everything seems legit. All right. So in this case, that's going to look like 1/2 12 root 2 minus 1.4 100 ohms times 1 volt times 60 hertz. So let's throw this in there. I get 1.0 0.297 millifarads. So our additional capacitance is just going to be 1.297 millifarads minus our 0.5 millifarads, or 0.798. With regards to the application problems that I could give you on an exam, this is literally about as hard as it can get. Really, the thing to understand is which of the three different ripple equations should you use based on which of the three different types of rectifier circuits we have. Donald, you look slightly confused.
So since you can't divide by zero, does that mean you're always going to have some ripple voltage? So you can never like truly convert AC to DC?
Yeah, you will always have some very, very small amount of ripple, right? Because the only way for you to not have some small amount of ripple is effectively this resistance to be infinitely large so that you just had an ideal capacitor. And if you never allow your capacitor to discharge, which literally cannot physically happen, that's the only way that you're going to get a pure DC signal out.
So the larger your capacitor, the smaller and smaller your ripple will be.
Yes.
And so you'll get very essentially close to a pure DC out.
But with a voltage regulator as the next stage, it's really not important. As long as your ripple is below 10% of your peak, that's usually good enough to be able to throw it into a voltage regulator. And then you would see only a couple of millivolts of variation at the output.
Which is what we just solved for, because having a 1 volt ripple.
Having a 1 volt ripple for a 15.571 peak is actually less than 10%. Yeah, it's around 7 to 8%, I think. Probably should be able to do that math better in my head, but let's call it 7 to 8%. Yeah. Our initial, excuse me, our initial of 2.595 volts, or about 1/6, so roughly 17%, we'd find that if we threw it in a voltage regulator circuit that was designed well, that'd probably be okay too, right? Because we saw for a 10 volt input with plus or minus 10%, we saw a variation of a fraction of a percent in the output voltage when we were defining and deriving our small signal model, right? So, I mean, as long as we're not seeing that the ripple is effectively half of our output signal, we should probably be pretty good to slap a voltage regulator on it and call it a day. And this is all assuming that, you know, all of our values have some very specific, or all of our components have some very specific value, when we all know that that's impossible, right? Components have tolerances, so even in our best case design, we're not going to have, you know, exactly 1 volt of ripple or something like that, because the values of the resistances and capacitors used aren't actually going to be exactly what we're specifying there. Just like the transformer isn't going to be perfectly ideal and all that kind of good stuff. So this is a best case guess as to how this thing is going to behave, which is what all of our mathematical models really are. All right, so this makes sense. Like I said, I'm going to give you a homework problem very similar to this. Something like this will guarantee be on your exam. This is, in my opinion, with regards to the diode application problems, this is as hard as it can get. All right, so let's very briefly talk about diode logic circuits. All right, so our options with diode logic are actually very limited. A diode is effectively a binary device, right? It can either be conducting or it can be non-conducting. So we can really only make two gates, okay? We can make an OR gate and an AND gate that delivers a digital output signal of approximately 5 volts or 0 volts. Now, we can expand those very slightly, and I'm going to have you do this in your homework assignment, by including an LED where the LED being on constitutes a digital high and the LED being off constitutes a digital low. The reason why you have to use an LED to get those other effects, a diode is incapable of inverting a signal. So all you can do is AND and OR. So to get NOR and NAND, you have to have some other way to represent that happening, because you literally can't get a negative voltage or whatever out of it, okay? So let's talk about the diode OR gate first. All right, so for a diode OR gate, will be a fairly straightforward circuit. We're going to have some input A. Down here, we'll have some input B. We'll tie the outputs of these diodes together and call this voltage V out. And then we'll have some resistance R here. And let's make what will effectively be a truth table for this guy. So this will be fairly straightforward, as there are only two inputs. And let's make a more conventional truth table here. Where we'll go 0, 0, 0, 1, 1, 0, 1, 1. And so for a 0, that means we're applying 0 volts to that pin. And for a 1, let's call it, we're applying 5 volts to that pin. Okay. So I've told you that this is an OR gate, so we should all know how the truth table is supposed to behave. But we could pretty easily verify this operation. So I need to put 5 volts down there at the bottom. My apologies. Okay. So let's start with the ideal diode model here. Okay. So if, ignoring the presence of this guy VB, or this diode VB at all for right now, so that we just had a diode in series with a resistor R. If we applied 0 volts to our input pin VA, what would we expect our output to be? Why do you say it's 0? So we are assuming here then, and I want to be clear about this, that this diode is off. So it's not necessarily reverse bias because it has the same bias conditions on both sides, but it's it certainly isn't on. Okay, right. So obviously the same would be true of VB in isolation, right? If we only had that diode, let's call this one DA and DB. We can say that when our input voltage VA or VB is 0, those diodes are off. It stands to reason then that if either of those input voltages, VA or VB, are 5 volts, we should expect to see that those diodes become forward biased, right? So they will look like a short circuit to a, for an ideal diode model, or a 0.3 to 0.7 to 1.2 volt drop, depending on whether we're using germanium, silicon, or gallium arsenide, right? So effectively, if, VA or VB is high, one of these guys is conducting, and so our output should be at 5 volts, because we're now able to drive some amount of current through this resistor R to force that output voltage to be non-zero, right? So the operation here is really all about making some current I happen, which flows through the resistor, thereby generating some output voltage, which is the drop over the resistor, right? So we should easily be able to see that when both of the inputs are 0, our output is 0 volts. When either of the inputs are 5 volts, for an ideal diode case, our output should be 5 volts. What if both of the inputs are high? Output's still going to be 5 volts. And so we get 0, 0, 0, oh, excuse me, 0, 1, 1, 1. Okay. So that's a diode OR gate. We could make more and more inputs just by putting more and more input signals and more diodes in, right? So I don't recall off the top of my head which of your design or how many inputs your design project for an OR gate specifies, but pretty straightforward. Now let's talk about the AND gate. It'll be very similar. We'll take our output at this leg of the resistor. So VA over here, VB over here. Now we're actually going to put our diodes in the opposite direction. And write our simple truth table. A, B, out, 0, 0, 1, 1, 0, 1, 0, 1, 0, sorry. A, V, B, B out. All right, go away thing. All right, so let's talk about how this guy works. It's gonna be very similar. So in order for our output to be high, or 5 volts, what needs to happen? This current up. Annabelle, you have any thoughts? Right. So our AND gate will output a high only if we're able to turn the current flowing through the resistor off, which means we need our diodes to be conducting or behaving like short circuits effectively, right? Because if our diode is behaving like a short circuit here, we would have a 5-volt potential on the bottom side of the resistor and a 5-volt potential on the top side of the resistor, making no current happen. But that's only going to be true if it happens to both of these simultaneously, right? So that's why this guy is an AND gate. So only when input A and input B, so if when input A and input B are high, both of these act like a short circuit. And so we're forcing this whole node to be high, which means there's no voltage drop over our resistor, and therefore the output is at 5 volts. Mr. Thigpen. No, so for an open circuit, let me think about this real quick. Right, yeah, okay, yeah, I see. So I got my nomenclature backwards. You're absolutely right, yeah. So when these guys go high, these guys turn into open circuits. There we go. So when they're open circuits, so we need these to be reverse biased. That's effectively what I'm doing. Thank you for correcting me. Yeah. So when these guys are low, they're conducting because it's 5 volts here, nothing here. And so that's going to pull the output down to 0. Absolutely right. Thank you. So when both of them behave as open circuits, which means they're both reverse biased or both at 5 volts, then we get the output we want. Thank you. So from this, we should see 0, 0, 0, and 5 volts, or 0, 0, 0. All right. So those are our two simple diode gates. Making logic gates out of transistors, to me, makes a little bit more sense because they work much better as switches, which is what all of this binary logic really should be. But you can, and early computers actually did use diodes for ANDs and OR gates because it was a much smaller way to implement them than using vacuum tubes. One of the biggest issues with using diode logic gates like ANDs and ORs is that you can really only have one stage of logic, because for a real diode where it's roughly 0.7 volts to turn things on or off, if you chain 1 or 2 stages together, you'll see that your output voltage is falling. Go away. By too much, right? So we know that for a real, we're not expecting the output voltage to exactly be 5 volts. We're expecting it to be above some threshold, which we call high, and below some threshold that we call low. Well, if we put too many stages together, the forward bias drop over the diodes will be enough to push a high signal into the interpreted as low range. So best case scenario, we can really only get 2 stages out of a diode-based logic circuit before we need to have some form of amplification involved. And the amplification involved comes from transistors. So with that being said, let's start talking about transistors. So the textbook that I have chosen for this class chooses, for whatever reason, to have its MOSFET chapter first. But that doesn't make a lot of sense to me. And because, as I expect, the overwhelming majority of you didn't even buy the textbook anyway, we're going to cover BJTs, right? In my opinion, BJTs are the more complicated of the 2 devices with regards to their analysis. So if we get a good grasp on how a BJT circuit works, when we get to MOSFETs, they'll be much more easy. Okay. Now, the theory of operation for a MOSFET is a little bit harder to understand, but you guys are all going to be engineers, so you largely probably don't care how it works, just why it works.
I'm just scared. If
That's fair. All right. So, introduction to bipolar, bless you, junction transistor, or more commonly known, BJTs. All right, so the first thing that I want us to talk about is their simple structure and their operational modes. So the name bipolar junction transistors actually kind of gives away what the device structure is. It is a bipolar junction. We actually have two options. We can go NPN or PNP. So we wind up getting effectively a sandwich of semiconductor material where the bread is of one type of semiconductor and the meat is of the opposite type. In a practical sense, how they're fabricated is going to look something like this. So let's say that this guy down here is an NPN BJT cross section. And over here on the right, we will do a PNP BJT cross section. And I'm giving you this cross-sectional representation for a very specific reason. And it's to illustrate the areas of the junctions are vastly different. So let me try to draw this real quick. So our middle region is what is called the emitter in both cases. And the emitter is what emits charge carriers into the device. Then we have the base. And we can think about the base as a knob. So there are always going to be charge carriers in the emitter region. But what our base does is effectively turn on or off the flow of those charge carriers through the device. And then finally, we have our collector, where, as the name implies, the charge carriers get collected. So for an NPN BJT, our emitter is very heavily N-doped. So I'm going to call that N++. And similarly for our PNP transistors, we have a very heavily doped P-type emitter. The middle of our sandwich, our base, is going to be heavily doped P-type for an NPN and heavily doped N-type for a PNP. And then finally, our substrates will be lightly doped N material for an NPN and lightly doped P material for a PNP. Okay. So when we do our analysis of what's going on internally in these devices, when we talk about the physics and everything, this isn't how we're going to look at that. But what I want to point out here, this is a cross-sectional area, okay? So the junction between the emitter and the base is three-dimensional, okay? It's effectively like the surface area of a bowl, all right? And then the junction between the collector and the base is the surface area of a bigger bowl, right? So effectively, the base is a pool of heavily doped N-type material in a PNP junction. And then the emitter is kind of a hot tub in the corner of that pool, if you will, right? So that the area of the base emitter junction is small, or is much smaller than the area of the base collector junction. Okay? Another very key thing about the operation of a BJT is that the width, or effectively the thickness of the base region, we're going to call the effective width, which means the thickness minus the width of the depletion region, which is going to have a depletion region on both sides, needs to be very, very thin, okay? And the reason for that should be fairly obvious, but if we forward bias our base emitter junction, right, we should see diffusion of charge carriers from the emitter to the base, because we just have a simple PN junction that's forward biased, right? Well, if the base is long, or has a large distance for our diffusing carriers to travel through, they'll all recombine before they hit the collector. So we want that base region to be thin so that diffusing injected minority carriers can actually get picked up by the collector so that we have some device current flowing through, okay? So that's why I wanted to talk about this three-dimensional kind of look at it. The illustration of those different areas is very, very important to the device's operation. And it enabled me to talk about the constraints on the width. All right. Yes. So the width of the base for a modern BJT is on the order of a couple of nanometers. So it's rather tiny. And the full reason is because we need to ensure that not all of our charge carriers recombine before they hit the collector. Because if they do, the amount of current that we could ever see flowing through this thing is going to be based on a very tiny recombination current instead of a reasonably large diffusion current that we can sustain with that base emitter voltage. Does that make sense? Okay. All right, so before we get into greater detail about what exactly is happening internally to a BJT, I want to talk about the 4 different modes that they can operate in. All right. So I'm going to draw a simple table here. And the mode is based entirely off of how those 2 junctions are biased. So we're going to have a cutoff mode. We're going to have what's called saturation. Then we have forward active. And then we have reverse active. Then we have to care about the base emitter junction and base collector junctions, relative polarity. So if both of them, the base emitter junction and the base collector junction, are reverse biased, we have cutoff mode operation. So effectively, if both of the junctions are reverse biased, it's obviously very, very hard to pass current in any direction through the device. Okay. So it acts as if the whole device is off. Okay. For saturation, we have the opposite condition, where both of the junctions will be forward biased. So with both of the junctions being forward biased, that means that our barrier potentials for current flow are as low as they can be throughout the entire crystal. And so current can easily flow effectively in either direction. It will want to flow more in one direction than the other based on the junction areas and the doping concentrations and things like that, but it can flow either way, okay? And so cutoff and saturation together, effectively fully off or fully on, if you will, are how BJTs are used in digital circuits. It's a switch, right? Either the junction is completely turned off or the junction is completely turned on, allowing, or the combination of junctions are completely turned on, allowing current to flow through. So these two guys are used in digital applications. Okay. Then we have the forward active region, where our base emitter junction is forward biased. So we are allowing diffusion from our very heavily doped emitter. So we're allowing charge carriers to diffuse from our very heavily doped emitter into our base region. And then we reverse bias our base collector junction, which effectively creates a large electric field, which sweeps those diffusing carriers through to the collector. Our reverse active region is literally the opposite. So forward active region operation is what is used in BJT-based amplifier circuits. So Class A, Class B, Class AB, Class D amplifiers are all reliant on BJTs operating in this forward active mode. Reverse active mode is effectively the same thing, but much more crappy because it's passing current in the wrong direction, right? We're taking a small amount of carriers from the lightly doped substrate portion or the lightly doped collector, diffusing them into the base, and then using a smaller field to try to sweep those through to flow out the emitter, okay? So generally speaking, we never actually use reverse active region to do anything because it's just doing the exact same thing as the forward active region, except smaller and much, much hotter, okay? So that's how you burn them out. All right, so now that we have discussed very briefly these four regions of operation, we're going to start our discussion on the physics of these guys by looking at the forward active region. We're going to look at the forward active region, and then we're going to look at the saturation region, and that's really kind of it. We don't need to look at the reverse active region because it's the same thing as as forward active, but worse. We don't need to look at the cutoff region because it's off. So there's nothing to look at. The device isn't doing anything. So I'm going to draw a fairly big picture here. And I'm going to talk through some things, and we're going to make little annotations all over this damn thing, okay? So let's consider, let's call this forward active mode operation. And we're specifically going to be dealing with NPN BJTs. And then, I don't know, something like next Friday, we'll circle back around to PNB BJTs and just cover everything very briefly. Our analysis here largely is going to be the exact same as a PNP BJT, except that we have a different type of carrier, charge carrier in the system, okay? So let's start by drawing a rather large sandwich structure. Okay. So I'm going to call this terminal up here my collector. And then I'm going to have a large collector region, which is doped N-type. Here in the middle of my sandwich is my base region, which is heavily P-doped. And this node over here is going to be my base terminal. And then down here will be my very heavily N-doped emitter region. And I'm going to put my emitter as ground in this very simplified example. Okay? For an NPN transistor, typically speaking, the collector should be at the highest point of electrical potential. The base should be at an intermediate point of electric potential, and the emitter should be at the lowest point of electrical potential for the transistor. So we could absolutely do things where, like, we connected a resistor down here or something like that as ground. That would effectively just shift the levels of everything up. But the emitter should be at lower potential than the base, should be at lower potential than the collector, at least for an amplification type application. Okay. So I am going to define a voltage here as VBE, which is the biasing voltage for the base emitter junction. So I'm going to call this guy right here BE to let us know this is the base emitter junction that I'm talking about. And over here, I'm going to have a voltage VCB, which is the bias voltage for the collector base junction. Okay. And I've drawn it in such a way that the positive polarity terminal of VBE is connected to the base, and the negative polarity terminal of VBE is connected to our N-type emitter, so that this guy should be forward biased. And based on the polarities of this guy, where the positive polarity terminal is on the N-type and the negative polarity terminal is on the P-type, this guy should be reverse biased, which is exactly the conditions that we need for forward active mode operation. Okay. So both of these voltages need to be greater than 0 volts for this guy to work correctly. All right. So if we draw, I'll do these in gray. So let's say that VBE is somewhere in the ballpark of 0.7 volts, which would be enough to turn that junction fully on. We should see a very small layer of bound positive charge on the N side of the base emitter junction. And because the P side is lighter doped, the width of this region should be a little bit larger. And we have a layer of bound negative charge. All right. This is going to give us a reduced barrier potential for our base emitter junction, such that EB, the electric field that is directed from the emitter to the base, is EEB naught, the unbiased field strength, minus what I'm going to call EF, which is the forward bias voltage, right? Or the electric field reduction due to the forward bias voltage. So that we have a relatively small electric field directed up at that portion of the device. You're scratching your head. Why are you scratching your head? Are you scratching your head because it itches, or are you scratching your head because you're confused?
I'm a bit confused.
Bit confused. All right. What are you confused about?
Why is it going upward?
Because it's directed from the positive charge to the negative charge. So that's why it's directed up. That's literally the reason. Positive charge is on the bottom, negative charge on the top, so the field is directed up. Wesley. EB naught. So effectively the unbiased electric field is reduced proportionally to the application of the forward bias voltage, which we discussed when we were dealing with PN junctions, right? The reverse bias conditions on the base collector junction are going to have a similar situation, right? We're definitely going to have a depletion region width. So we are going to have, and because of the light doping here, we're going to have another layer of bound negative charge here. This width is going to be reasonably wide because our collector is very lightly doped. So we have bound positive charge on this side. And when we put those two conditions together, we have an electric field E, and this will be going from the collector to the base, and it will be ECB plus ER. So it's being enhanced by the reverse bias voltage. So that makes, whenever we reverse bias a PN junction, it makes the barrier potential larger, which means we have a larger electric field directed down, right? So it's still going from positive charge to negative charge, but because of the sandwich structure, the positive charge is up here in the collector, the negative charge is again in the base because of the way that they're doped. All right. Okay, everybody with me thus far? Sorry, that should be EC. Dang it, go away. Yeah, ECB naught. Thank you. Yeah, so the unbiased value being enhanced by some reverse bias voltage. All right, so let's focus the next couple of minutes here on what's going on at the base emitter junction. All right.
A larger electric field downwards.
Yes, significantly larger. Yes, absolutely. which is why this arrow is teeny tiny and this arrow is real big. That was my goal. Wesley. No, so not nearly that much. So if our substrate doping is somewhere in the ballpark of 10 to the 12, then our base might be up to 1,000 times more heavily doped, and our emitter might be up to 1,000 times more heavily doped than that. So it really doesn't have to be that large. We could get away with, like, 10 to the 12, 10 to the 14, 10 to the 16 kind of thing, but it does need to be at least an order of magnitude larger, for reasons that we'll talk about in a couple of minutes, if they haven't been clarified already. All right, so let's talk about what's going on at the base emitter junction. We should have electrons diffusing into the base, right? So they're going to start here in the bulk of the emitter, and they're going to wind up on the opposite side of the depletion region of the base emitter junction, and they are going to diffuse through this region, which we'll talk about in a moment, right? So we know how the electrons are behaving. We have electrons coming from the emitter and diffusing across that reduced barrier potential, winding up in the base region. And similarly, some holes. I'm going to call this H plus. Holes are going to diffuse from the base into the emitter. Right? Now, because the emitter is much more heavily doped than the base, we should see that this current through this region of the device is largely dependent on the behavior of electrons, right? Because there are way more electrons than there are in the emitter than there are holes in the base, at a large degree. Okay. So this carrier diffusion across the base emitter junction is going to yield a current, which I'm going to call IE. What direction should IE be, based purely on the diffusion directions here? If electrons are moving up, positive current is going down. So we have an emitter current, put it over here, IE flowing down or out our emitter terminal. We should have a fairly reasonable idea of what this emitter current is going to look like. What I mean by that is that we have diode operation for this base emitter junction. So we should expect that it's going to be, I don't know, some sort of saturation current type quantity being multiplied by E to the VBE, which is the forward bias voltage of that junction, divided by VT, the thermal voltage of that junction. So it's going to behave generally proportional to the exponential of VBE over VT. We'll flesh out the details of what number goes in front in a little bit. Hayden, are you raising your hand? Okay. What does your shirt says? Mass, force is equal to mass times acceleration. Oh,
Yeah.
You're 5 months too early. It's okay. I like it anyway. I said because May the 4th would be, yeah, sorry. All right. Okay, so all right. Sorry, I had to collect myself here. All right, so we have these electrons that have diffused from the emitter into the base. Since the width of the base, as we've talked about, is fairly small, we should see that a large portion of these diffusing electrons will get swept across to the collector by this large field. But a small portion of them will wind up recombining. So I'm going to try to depict that as such. So this arrow directed to the left represents the portion that winds up recombining. And then this guy up represents the portion that survives. So these are just more electrons. We have electrons diffusing from the emitter through the base and then being swept through into the collector region. So this is going to yield a collector current that is dependent only on the number of electrons that have survived, because there shouldn't be any hole injection or anything like that happening, right? So our collector current, I'm going to write it down here, will be IC is equal to AE, which is the cross-sectional area of the emitter or the base emitter junction, which is why it was so important to see that our junctions have different sizes, multiplied by Q, the charge, the elementary charge, Dn, which is the electron diffusivity in the base region, times Ni squared, divided by NB WB, where NB is the dopant concentration in the base region. So this is just simply the number of acceptor atoms there. And then WB is the effective width of the base, which I'm going to define that real quick before we move on with this equation. So the effective width of the base is the distance between the edges of the depletion regions observed in the base. Okay. We are, for right now, going to consider this quantity to be a constant, with the understanding that once we know a little bit about how these guys behave, a little bit more about how these guys behave, we're no longer going to treat it as a constant. Okay. And I'll talk about what exactly that will mean in just a second. I'm going to multiply this coefficient out here by exp of VBE over VT. Okay. So what this guy represents is our saturation current that tells us effectively how many electrons survive diffusing across the base and get swept into the collector, okay? Which should mean that it's fairly obvious why it depends on the diffusion coefficient for electrons in that region, why it depends on the number of acceptor atoms in that region, because that's effectively giving us the probability of recombination occurring. And then the width is also important because that's also related to the survival of moving to the electric field and getting swept through that junction. Okay. So as a very, very brief aside here, as the collector base voltage VCB gets larger, what happens to WB? It gets smaller, right? Because the size of this depletion region is going to expand, which lowers WB, which in turn causes this quantity IS to increase, which forces our collector current to increase. This is what's called the early effect. Okay, we're going to talk much more about this in a couple of days. So you don't need to actually write any of this crap down yet. I just wanted to explain what's going on here and why our assumption that WB is constant is actually incorrect. It's going to make the math easy for describing what's going on, but it's not entirely true. Okay, so our collector current IC here, ignoring the effect, the early effect, shows that our collector current is independent of the base collector voltage or the collector base VCB, so the collector base voltage, right? So the amount of current flowing in the collector depends on the voltage drop over the base emitter junction at a first order look at how this system is behaving. Okay. So it should be fairly obvious. This is going to result in a terminal current of IC flowing down, right? Because if the electrons are flowing up, the positive current is flowing down. So the next thing that I want to talk about is what the base is doing. Okay? And so to talk about what the base is doing, we need to look at this guy from a function of it behaving at steady state, right? So steady state isn't thermal equilibrium. Steady state is maintaining what is happening, right? So we have the positive polarity terminal of a voltage source connected to this base. We have a negative polarity terminal of a voltage source also connected to that same terminal. What the base terminal is doing is maintaining the level of hole diffusion from the base to the emitter while also maintaining the level of recombination occurring in the base so that the collector current is effectively a constant value. Okay, so we should see, I'm going to try to draw this as like this so that we see some portion of those diffusing holes are coming from the base terminal. We should also have holes being supplied to recombine with injected electrons from the emitter such that overall we observe a base current IB flowing into the device. Okay, so it's just adding holes from our voltage sources or adding positive charge from our voltage sources to make this sustain a particular collector current. Okay. The base current is typically expressed as a fractional portion of the collector current, where we can call IB simply IC divided by a value beta. Or alternatively, this would just be IS over beta times EXP VBE over VT. Beta, put it over here, is what's known as the common emitter current gain. So let's talk very, very briefly about what that means. Okay? The system that we have described right here would be a common emitter system because the emitter is literally tied to the common terminal ground. Okay. So what beta represents is a very specific view of the operation of a BJT. And this view effectively says that the base current IB is the controlling factor of the amount of current that flows through the collector. And beta just represents that transfer of a small amount of base current multiplied by beta gives you a large amount of collector current. So that's why it's the common emitter current gain. Okay. By definition, it will be the ratio of IC over IB in the forward active region. And I'm making that clear because when we talk about saturation mode operation, there will be a beta or a common emitter current gain, but it will not be defined in the same, well, actually it'll be defined in the same way. It'll be IC over IB, but we'll find that it's going to have a smaller value. And it represents effectively the same thing, but you know, we'll talk about it in a bit. Another way to represent beta, which you see this in data sheets, HFE. Okay. Write it down. So this is equal to HFE. HFE, and you guys are juniors, so you probably haven't had any, or a small amount, if any, network theory to this point. But this is what's known as a hybridized parameter that literally just relates the output current or the collector current to the input current, which is the base current. So this is literally the exact same definition as beta. But for whatever reason, data sheets give you HFE as a hybrid parameter instead of just using the symbol of beta. They literally represent the exact same thing. Okay. Textbooks, for whatever reason, use beta. Data sheets, for whatever reason, use HFE. They're both simply the collector current divided by the base current during forward active region operation for BJT. Okay. Typical values for beta are anywhere between 10 and 1,000. 50 to 200 is kind of the sweet spot of where they usually fall, but it's not unheard of for them to be as low as 10. It's not unheard of for beta to be as high as 1,000. So I'm going to wrap things up here very, very briefly, and then we'll probably recap with a, when we get in on Monday with a recap of all of these relationships. But it should be fairly obvious to see, just applying Kirchhoff's current law, that our collector current plus our base current combine together to form our emitter current, such that IE is equal to IB plus IC, or beta plus 1 over beta times IS EXP VBE over VT. So what I want to talk about at the very beginning of Monday's class is introducing a second transistor parameter. So it's kind of the complement of beta, which is called alpha, and it is the common base current gain, and then how it relates to these equations, and then we'll move along from there. So we've effectively well described, at least in my opinion, you may disagree, the operation of a BJT in the forward active region and understanding all of the different mechanisms for why currents are flowing in the directions that they do and all that kind of good stuff. So I believe there is a small issue with the homework set that I put up yesterday, in as much as I forgot to include IS values for the diodes when you're using the exponential model. So I will get that rectified in the next couple of minutes. I'm literally just going to go upstairs and write IS is equal to 5 times 10 to the negative 15 and call it a day. But I just wanted to let you guys know that, since your homework, I believe, is due after the break or after the weekend. All right, thank you guys.